Hello everyone, my name is Kunal and I'm your physics tutor and we are actually doing oscillatory motion and today is our lecture number 8. So let me recap the things कि हमने previous class में क्या क्या चीजें cover करी थी. So in previous class we actually deal with miscellaneous system जिसमें हमने time period निकाला था and we actually deal with the actually we learned about the finding the time period using energy method जिसमें जो मेनली चीज हमें करनी होती थी वही करना होता था कि डिस्प्लेस पोजीशन पे एट डिस्प्लेस्ड पोजीशन we have to write the total energy and then we have to differentiate it with respect to time which is actually equal to kinetic energy plus potential energy which is actually total energy is. And we have to differentiate it with respect to time and equate it to 0. That means dke by dt plus du by dt is equal to 0. And we have to reach to a relation which is something like a is equal to minus of omega square x. Okay, and as we get the equation, we actually get the omega value and then the time period is equal to nothing but 2 pi by omega. So this is the how we approach in finding the time period using the energy method. So अभी तक मैंने जितने भी सिस्टम पे हमने बातें करी हैं वो एक्चुअली लीनियर सिस्टम था, राइट, जिसमें सिंपल हार्मोनिक मोशन जो है, जो ऑसिलेटरी मोशंस हैं, वो एक प्लेन में हो रही थी, लाइक इन वन प्लेन में हो रहा था. लाइक अगर मैं इस सिस्टम की बात करूं या फिर अगर मैं इस सिस्टम की बात करूं, जितने भी सिस्टम हमने डील करी है, राइट, इट इज एक्चुअली हैपनिंग इन दिस स्ट्रेट लाइन. बट in today's lecture we are going to deal with some angular simple harmonic motion kind of thing. So let's start our today's topic. So actually we are going to start our today's topic, which is actually angular FHM, which is actually simple harmonic motion. Okay, so as we actually learn in normal simple harmonic motion, where actually our restoring force is actually equal to minus of k. So in angular SHM, we have to only take their analog. So actually, when we take the analog of force, it will be like torque. Restoring torque. Let me write it here. I'm just taking the analog of simple harmonic motion. So actually, it is restoring torque. And the k will be same because it is actually spring constant or anything, so it will act as a constant. But when we talked about in SHM, there is like displacement from mean position, right? But here actually same displacement thing, but there is actually angular displacement. So here theta is nothing but angular displacement of oscillator from mean position. Right. So theta is nothing but the basically what I'm doing here, I'm just taking the analog of the simple harmonic motions. So in angular simple harmonic motions, the force is actually replaced by torque, restoring torque, and the displacement from its mean position, which is actually x, is actually replaced by angular displacement of oscillator from the mean positions. Right. So this is the thing that you have to do here. So similarly, similarly here, we can write torque is equal to moment of inertia into alpha, where let me write it here. I is actually moment of inertia. Same as we do here for restoring force, mass into acceleration. So mass, the analog of mass in rotation is moment of inertia. And the analog of acceleration in rotation is actually angular acceleration. So here the moment of inertia and alpha is actually angular acceleration. So here we can write I alpha is equal to minus k theta, and we have to get the relation between, in SHM we have to get the relation between AR and X, right? So here we similarly here we have to find the equations between angular acceleration and the angular displacement. So actually minus k by I into theta, right? So this is actually our omega square term. So our omega square is nothing but k by I. So that's imply omega is equal to root under k by I, right? So our time period is nothing but 2 pi root under I by k. If you notice here one thing, nothing is changed. As in simple harmonic motion, our time period is 2 pi root under m by k, right? In simple harmonic motion, right? Similarly, here I just take the analog of mass in time period also. It actually the analog of mass is moment of inertia in rotation. So I'm just taking the analog here. So our time period is also in the form of 2 pi root under I by k. So let me recall once. So no, अभी तक जो भी हमने सिस्टम देखी थी वो एक्चुअली इट्स मूव इन अ वन प्लेन. Right now we are actually we have to deal with the system like simple actually simple pendulum kind of thing. Okay, so here the motion is in actually 2D plane, right? So and we have to like there is no displacement from its mean position of kind of thing, right? And this is actually the simple pendulum is actually the example of angular simple harmonic motion, right? So what we have to do, we have to derive these equations which we actually correlate to the simple harmonic motion. So what I'm doing here, I'm just taking the analog of linear motion to analog of rotational motion. So that's why I'm using the analog of mass in moment of inertia in for rotation kind of thing, acceleration, angular acceleration, force, torque. Okay, displacement. So there will be like angular displacement. So that's why I am just taking the analog of restoring force. It will be like restoring torque, displacement, angular displacement, right? And the same thing I do here because we have to do like mass into acceleration and we have to get the relation between acceleration and the displacement from the mean position. So the same thing I'm doing here. AR is equal to minus omega square x. And so here like I alpha is equal to minus k theta. I is our moment of inertia and we get actually relation between angular acceleration and the angular displacement. So here will be like omega square is equal to k by I. So we all know that the time period is nothing but 2 pi by omega. So our time period is 2 pi root under I by k. Here we can also analyze one thing like in simple harmonic motion, the time period is just 2 pi root under m by k for single spring mass system. Here also the time period is just mass, just I take the analog of mass here like 2 pi root under I by k. So now let me tell you here something. Like let's take a system. This is actually our S suspension point. Yeah, right. Let me draw it below so I can do it here. Okay, let us suppose this is actually our S. This is actually suspension point. Okay, and this is actually our. Let me tell you. This is actually a mass you can say, and this is actually our mean position, right? And this is actually our angular displacement. I'm called as theta naught, right? And this is actually EP, which is actually termed as elongated position, or we can term as extreme position. So here mostly we like extreme position because elongation and subtraction is kind of thing happening in the spring. So this is actually termed as extreme position. Similarly, when you left it goes to the same displacement theta naught. This is the another EP, which is actually extreme position, right? And it is actually, if you left it from here, so it goes there and it goes, right? So let me tell you one more thing here. If you notice one thing, I draw the simple harmonic motions graph, so it will be like this, right? One complete oscillation. But in this case, we are actually dealing with something like this. First, I'm starting from there, I goes there, then from here, you can do like this, right? So if I can draw there, this is actually our extreme position. This is actually our mean position. Look at this. is first going from elongated position to mean position. If I'm left from this point, A point, then mean position to elongated position, and then return back to the EP to MP, and then MP to EP. This is actually both of them, both of the figure representing the same thing. And what it is? It is actually one complete cycle, right? Now I'm gonna write some of the equations here. Okay. Now I'm gonna write some of the equations here. So it will be equations of angular simple harmonic motion. जैसे हमने उसमें डिराइव करी थी सारी इक्वेशंस, तो यहाँ पे मैं एक इक्वेशन लेता हूँ. The x is equal to, we actually derive a sine omega t plus phi, right? So what I'm gonna do here is I'm just taking the like x is displacement, so I'm gonna take it as the first equation, which is actually analog, obviously for angular simple harmonic motion. X is termed as, this is actually displacement, and we have to write it here angular displacement. So theta is equal to theta naught initial angular displacement and sine omega t plus phi, right? Now we have to find like angular velocities, angular acceleration and all. So let's derive it by differentiating it. So second equation, like angular velocity. So angular velocity is something represented by this, and it is actually equal to d theta by dt. So when you differentiate, what you get? Theta naught omega cos omega t plus phi. The third thing we have to derive is angular acceleration, d psi by dt. Obviously, because like dv by dt, so here will be like d psi by dt. You can call it omega, whatever, like alpha is equal to 2 d omega by dt. And when you do so, it will be like minus theta naught omega square sine omega t plus phi. Fourth, torque is equal to I into alpha, right? So here the I is, you can write as according to the given figure, and alpha is actually here, right? So we can write theta naught omega square sine omega t plus phi. So these are actually, I'm writing the equation as a function of time. एंगुलर डिस्प्लेसमेंट एज फंक्शन ऑफ टाइम. देखो मैंने बस क्या करी कि मैंने बस डिस्प्लेसमेंट जो हमने सिंपल हार्मोनिक मोशन में डिफाइन करा था उसका बस रोटेशन में, बिकॉज एंगुलर simple harmonic motion, that means there is actually happening some kind of rotations, right? So मैंने क्या किया कि just taking the analog of the displacement, so it will be like angular displacement, just taking the analog of acceleration, so it will be angular acceleration, the same thing angle. And I just take the one equation, which is x is equal to a sine omega t plus phi. So it will be like theta is equal to theta naught sine omega t plus phi, and just differentiating it. So these are the equation which is I am deriving as a function of time. Now let's move to the next equation, which is actually rotational kinetic energy, right? We have to find the as a function of time. So what it is, half I psi square omega square, and half I, what is actually omega? So here will be like theta naught square omega square cos omega t plus phi. Sixth thing, you have to find like potential energy. So what is actually potential energy is nothing but half k. There will be like half k x square, and there will be like half k theta square. So half k, and what is theta here? So here theta is actually theta naught sine omega t plus phi. So half k theta naught square sine square omega t plus phi. And what is actually our total energy? So our total energy is rotational kinetic energy plus potential energy. And when we add this both of the, so what we will get? We get half I theta naught square. Let me add it here. Cos omega t plus phi plus half k theta naught square sine square omega t plus phi. So if you look at this both of the term, right? So look at here. actually omega square is equal to k by I, right? Omega square is equal to k by I. So I omega square is actually equal to k. So these both term making it as k. So half k, I'm using this. So half k theta naught square, and here will be like in cos square here. So cos square omega t plus 5 plus half k theta naught square sine square omega t plus 5. Right. So it is actually equal to when we take half k theta naught square as common. So it's like cos square omega t plus 5 plus sine square omega t plus 5, and this both making it as 1. So it is actually equal to half k theta naught square. It is actually total energy, which is actually independent of time and displacement, right? As we get in simple harmonic motion, half k a square as total energy, and here also we are getting half k theta naught square, where actually theta naught is our initial, basically angular amplitude, you can say. So yeah, this is actually independent from time, right? Okay. So now on, we have to deal with some kind of system, which is our first system. It's simple pendulum, right? So let's begin it with your system. So let's take it as this as suspension point, and this is actually our wall. So पहले simple pendulum होती है. I hope you all know about this. कि there is a string which is actually attached to a small mass. Let's call it as mass m, and the string has length. Let's call it as L, and this is its actually mean position. And what I'm gonna do here is I'm just taking it from mean position as a theta angle. Okay, and I just left it from here, right? So what you have to do here, as we have to find the time period of the simple pendulums, right? Let me write it here. Okay, we have to find the time period of the simple pendulum. So as we all know, we have two methods. The first method is force method, and the second method is energy method, right? And when you recall the force method, what we have to do, we have to write the all of the equations at mean positions. So, and we have to write the all of the equations at displaced position. And then we have to, using the two equations, we have to write an equations accelerations as a function of displacement from mean position. So here same, we have to write the angular acceleration as the function of angular displacement, and then we find the omega square, and then we are able to calculate the omega naught, right? Basically time period. So the same thing we have to apply here. So we are actually using force meter. So this is actually our extreme position or displaced position. So here actually we are going to deal with its dynamics. So actually mg force is acting vertically downward, and there is actually a tension force here, right? And when we take its component, so in this direction it will be like mg sine theta, and in this direction actually mg cos theta. If we just take the it's so there is actually theta, so this is actually theta. So actually this is actually theta, so it will be like mg cos theta, right? So this is actually theta, this is theta, this is theta, and this is actually 90 minus theta. So mg, this angle is also theta, right? Let me write it here, theta. So this angle is theta, so mg cos theta, mg sin theta. Okay. Now what we have to write? We have to write, because there is no net force on the system, because mg is downward and tension is upward. So both of the force are anti-parallel. So net force on the system is 0, right? So here at you can write at mean position, like mg force is acting vertically downward and tension force is acting vertically upward, and both of the force are anti-parallel. So obviously restoring torque is 0. Now here we have to write the at displaced position as as I'm taking the uh, restoring force in this SHM, so in angular SHM, we have to take the restoring torque. So at displaced position, at displaced position, or you can say, mostly you can say extreme position, right? So at extreme position, you can say like torque restoring is equal to, let me show you here. This is actually length as L, right? This whole length as L. So mg L sine theta, and it is actually acting in this direction. So you can write torque is equal to minus mg L sine theta, right? And motion is oscillatory. Now look at here. If this theta is less than 4 degree, okay. So we know an approximation like sine theta is equal to theta, right? Here the motion is actually oscillatory motion. But we all know that when the theta is much, much less than, then sine theta is equal to theta, right? So when theta is at, this is actually approximation. Let me write it here. This is nothing but it is actually approximation. We are doing some approximation, right? Because if you take the in general case, we have to find the relations between uh, angular acceleration and angular displacement, right? And here we get the sine theta term. But this motion is actually oscillatory. It's not simple harmonic motion, right? Because in simple harmonic motions, the force is actually the function of linear function of uh, displacement from its mean position. So similarly, if you take its analog, so in angular simple harmonic motion, torque is the linear function of angular displacement. But here actually, when you considering the system, right? So here actually it's not the linear function of angular displacement. Restoring torque is not the linear function of the angular displacement. So this motion is not angular simple harmonic motions. So we have to do and we have to assume one approximations, and the approximations is we are considering that the theta is actually much, much less than 4 degree. So now on, we can write if the theta is less than 4 degrees. So we can write our restoring torque as minus mgl theta. Now this is actually our angular simple harmonic motion, because restoring torque is actually linear function of angular displacement. So here this term is actually our omega square term. Not now, because we have to write in the form of like I into alpha. So you have to do here. So in this case, it's the moment of inertia is ml square about suspension point. So I about suspension point is ml square. So here you can write alpha is equal to minus mgl theta by ml square. So when you do so, you will get alpha is equal to g by l into theta, right? And this is actually our omega square term. So our time period is nothing but 2 pi root under L by G. Because time period is nothing but 2 pi by omega, right? So our omega is from here is G by L, root under G by L, obviously. So it will be time period 2 pi root under L by G. So here we get one thing, time period for simple pendulum is actually 2 pi root under L by G. I hope you all know this formula, but derivation somehow you know, but some people know and some people not. So actually this is the derivations of time period of simple pendulum, right? And its formula is 2 pi root under L by G. Let's take a quick question here. So, okay, so let's take a question here. We are actually given is percentage increased in and length is equal to 44%. Then you have to find the time period. Basically, change in percentage change in time period. Okay. So look at here. Actually, our length is increased by 44%. So let us assume here our initial time period with normal cases with length L is equal to like 2 pi root under L by G. Right. In normal situations, its time period is nothing but 2 pi root under L by G. Now what I'm doing here, I'm just increasing the length by 44%. So now our L dash is equal to L plus 44% of L. So it will be like 144 L by 100. Right. So our new time period, which is actually T dash is 2 pi root under 144 L by 100 G. And it is actually equal to 1.2 into 2 pi root under L by. So you can write it here. If I'm calling it as T, so it will be like T dash is equal to 1.2 T. Right. Now we have to find the percentage change in the time period. So here, first you have to find the change in time period, or you can find, so the change in delta T, T dash minus T, it is actually 1.2 T minus T, it is actually 0.2 T. Now percentage change, if I am talking about percentage change in time period, so it will be like del T by T into 100. Right, so 0.2 T into T into 100, so it will be like 20%. So if you increase the length of the simple pendulum by 44%, its time period is actually increased by 20%. Right? That means as you increase the length, its time period increases. And as your acceleration of gravity decreases, right? As your acceleration of gravity decreases, your time period is actually decreases. No, as your acceleration of gravity decreases, your time period increases. And as your acceleration of gravity increases, your time period decreases. Okay, so this is actually some problem based on it. Now you have to draw a graph between time period versus L. Because G is somewhere constant in the planet Earth. If you change the planet, like if you are measuring in on the uh, Earth and then you measure the same oscillations on Moon. So, and you all know that the acceleration of gravity on Moon is 1/6 of the Earth, whatever on the Earth. So they are like acceleration of gravity decreases, so time period obviously increases, right? Now yes, draw the graph between time period versus length. So as from above expression, you all know that the time period is 2 pi root under L by G. If I am considering like time period is 2 pi by root Z and root L. This term has constant, something constant K. So we have like time period is equal to K root under L, right? And when you draw the graph of this section, so it will be something look like, let me draw it here. This is actually our time period and this is actually our L. So it will be like y is equal to root x, right? So it will be simply, so this is actually the graph between T and L. Now I'm going to discuss about some special kind of simple pendulum. This is actually known as second pendulum. So second pendulum. So actually simple pendulum having time period 2 seconds. This is actually known as a simple second pendulum because it is the actually simple pendulum, same like simple pendulum, but it has a time period of 2 seconds. So which simple pendulum has a time period 2 seconds? Let me let me do it here, some calculation and so you. So here like time period is 2 pi root under L by Z, right? And for second pendulum, the time period is actually 2 seconds. So 2 is equal to 2 pi root under L by Z. Just get cancelled. 1 is equal to pi root under L by G. So like 1 by pi is equal to root under L by G. So 1 by pi square is equal to L by G. Squaring both sides. And there is something like pi square is approximately is equal to G. Right? Yeah, pi square value is approximately is equal to. So here the length is equal to actually 1 meter. 1 meter. Right. So if you take a simple pendulum of length is equal to 1 meter, so its time period is actually 2 seconds. Right. Its time period is actually 2 seconds. You have to note one thing. The pendulum clock of time period 2 seconds. Pendulum clock. If you take the length 1 meter and it is actually attached, this pendulum is actually attached to your clock. So its time period is actually 2 seconds. So pendulum clock of time period 2 seconds. Right. Now we are gonna calculate some time period of the simple pendulum with other forces actually acting also, right? In this case, in this normal simple pendulum, we have actually one force acting on the system, and that force torque is actually um, force of gravity, right? mg force. But what if some other force also acting on the pendulum, right? We have to consider this. What if some other force also act on the system? So let's take a system. Uh, take it as question, right? So take it as question 2. So this is actually our lift. Okay. And what I'm doing here, lift is actually going upward with acceleration a naught. And what I'm doing here, from its ceiling, I take a string and attach the mass M, and length of string is L. And then I'm telling you, okay, find the time period of simple pendulum, because it's actually simple pendulum, but right now it's actually attached in, देखो ये सिंपल पेंडुलम है जो लिफ्ट में लगा दी गई है, ठीक है. Now you have to find its time period. Is it actually equal to 2 pi root under L by G as we derived earlier here, or its value is something different, right? So you have to find it out. Now what I'm doing, I'm attached the same simple pendulum to the ceiling of the lift. Now look at it. What we have to do, we have to first write the equations at this mean position. So actually there is two force actually only acting mean position. So actually mg force is acting downward and a pseudo force due to lift, because actually lift is going in upward direction. So the pseudo force is actually acting on the downward direction and the tension upward. So here the actually restoring torque is 0. Now at displaced position or at extreme position, mostly you can use extreme because displaced position is something like you connect it to string. So what I'm doing here is at extreme position, if I'm taking this like this ceiling of lift, so at displaced position, this is actually our mean position. This is actually our displaced angular displacement. And this is actually, there is some force acting mg plus ma naught vertically downward. This is actually force due to gravity, and this is actually pseudo force. Similarly, in this direction, we have, when you take the component, in this direction, we have force. mg plus a naught sine theta. And due to this, torque is actually happening. So our restoring torque is actually is equal to minus mg g plus a naught sine theta, right? And we all know that we have to this motion is actually oscillatory motion, and we all know that we have to consider the angular simple harmonic motions. So for that, and in angular simple harmonic motions, the restoring torque has to be a linear function of angular displacement. So we have to use a approximation here, and that approximation is theta is uh, less than 4 degree, right? So when you do so, it will be our restoring torque is actually equal to minus mg. There will be like L also. So mg plus a naught L theta. So this is actually our alpha is equal to minus mg plus a naught L by ml square into theta, because the same, the moment of inertia is remains same, which is ml square. About suspension point, I about suspension point is remains same, it is ml square. So here we get the relation between angular acceleration and the angular displacement. Let me simplify it. So here we'll get alpha is equal to minus a naught plus g by L into theta. So this is actually our omega square. So here omega is equal to nothing but root under a naught plus g by L. So that's imply our time period is nothing but 2 pi by omega, and it is actually 2 pi root under L by a naught plus g. So here our time period is actually decreased because our numerator is actually increased. So overall the time period is decreased. So from, you can say from normal simple pendulum, here time period is actually decreased. Time period is decreased, right? So I hope this all will be clear to all of you. So now in next class, we are actually dealing with some other kind of system like simple pendulum in accelerating car, and and we are doing some problem based on it, because in today's class we are mostly dealing with the theory, right? So okay, that's all for today's. Thank you.